Welcome to the Get Started tutorial for the A Pathfinding Project. This package focuses on 3 things it can do for your game. It allows you to generate a nav mesh from your game world. It can plan paths for how to get from one point in the world to another point. And finally, it has included movement scripts to allow agents to follow those paths. In this tutorial, you'll learn how to set up pathfinding in a simple scene, together with an agent that follows your cursor around. If you prefer text rather than video, there's a link to a text tutorial in the video description. If this is your first time using the package, you will have to install it first. Assuming you have purchased it using the Unity Asset Store, then you can open up the Unity Package Manager, go to My Assets, click the asset in the list, then click Download, which should only take a few seconds, and then click Import the project. Unity will pop up a window that shows you exactly what is going to be installed. You can just click Import. But you may note that the package is going to be installed into the Packages folder, not your normal Assets folder. The first time you import the package, you'll be greeted by a welcome message. From here, you can easily import the included example scenes, or access the Get Started guide, which really is this video, access the changelog and see what the new updates are, or access the rest of the documentation. If you happen to close this window and you want to import samples later, you can do so via the Package Manager. However, at the time of recording this video at least, the Package Manager has a slightly confusing UI for this, so let's go through it quickly. You must go to the In Project tab, and then click on the A Pathfinding Project entry. However, you may note that there are 2 entries in this list, so you have to choose the one with the custom tag on it. Then you can go to the Samples tab and click Import. If you want, you can pause the video here to explore the example scenes before continuing. Now, let's create a new scene to add some pathfinding to it. We'll go to New Scene, and then we'll just use the default Unity scene. And click Create. And now the first thing we need is to add some kind of ground for the agent to stand on. So we'll create a plane and position it at the origin, and perhaps scale it up a bit too. Then, of course, we might want to add some obstacles for the agent to avoid. So we'll create a cube and position that somewhere around the origin as well, and let's scale it up a bit too. And we can create a few more by just duplicating them using Ctrl-D, and maybe taking one and scaling it a bit to get some variety. Like that. Alright, I have actually created a few materials for this scene, just to make sure that not everything should be all white and boring. So I'm just going to add those right now. Like that. Much prettier. Now we are ready to add some pathfinding to this scene. And for this, we'll need a graph. A graph is a description of the traversable surface of the world. More precisely, it describes all locations where the center of the agent is allowed to be. In this package, all graphs are added to a single component called AstarPath. So let's create an empty game object, name it A*, and then add the AstarPath component to it. This is a singleton, which means that you should only have one instance of this component in your scene. The inspector is, as you can see, divided up into sections. The top section contains all your graphs. Most games will only have a single graph, but you can add more if you want to. This package contains several types of graphs. There are grids, manually created nav meshes, for example in Blender, automatically created nav meshes, and a few others. The second section contains all the global pathfinding and logging settings. There is, for example, a setting for how many threads to use for pathfinding, some heuristics, and logging options, and so on. The third section has options for saving and loading graphs to files. You see, normally you will calculate all the graphs when the game starts. However, if you have a large world, this may take quite some time, so therefore you can cache the graph to make sure that you can just load it when the game starts, which will be much faster. The fourth one is called optimizations, and it has project-wide options for enabling or disabling features. You usually don't have to touch these, but they can sometimes give you a slight performance or memory boost. The final one is called the About tab, and it has some handy links to the documentation, and you can also see which version of the package you are using. Finally, There is the Show Graphs toggle, which shows or hides the graph in the scene view. Right now we don't have a graph at all, so nothing is shown. And there is the Scan button. This is used to scan or calculate all the graphs, and you can also do that using a shortcut, Ctrl-Alt-S on Windows or Command-Alt-S on Mac. So let's add a graph to the scene. For this tutorial, I'm going to show you how to set up a Recast Graph. As mentioned earlier, this package contains several different types of graphs, and you can read more about the other types in the online documentation. The Recast Graph generates a nav mesh automatically from the world, and it's a pretty good solution for most games. So we'll just go ahead and create a Recast Graph. So you can see the bounding box that was created here, and if we click on the graph, we will bring up its settings. Now we can actually pretty easily make this into a working graph. The only thing we want to make sure is that the bounding box covers our world. It already does this in this case, but if it doesn't, we can click the Snap Bounds to Scene button. This will modify the bounding box so that it covers all of the objects here. Now we can either scan the graph using the button down here, or we can do it using the shortcut Ctrl-Alt-S or Command-Alt-S on Mac. And there we go. This blue mesh that you can see here, this is the nav mesh, which, as I mentioned earlier, represents the part of the world where the agent can walk. Now, you may be wondering what actually happened, so let's quickly explain what the Recast Graph does behind the scenes. The Recast Graph takes as input all of the colliders or meshes inside of this bounding box. Then it converts these into a voxelized representation, and you can think of this as kind of like a Minecraft replica of the world. Minecraft is made out of lots of boxes, and it's kind of the same here, just that the boxes are a lot smaller. Of this, it does a bunch of post-processing on the voxels to try to figure out where the agent could possibly stand, and then as a last step, it triangulates it into a mesh, and that is what you can see here. The Recast Graph has a lot of settings, but I'll take you through the most important ones. At the top, you can set the bounds of the graph, so you can change the center, the size, or even the rotation of the graph. And of course, you can also snap it to the scene if you want to. Next, there's input filtering. So you can filter which objects are taken into account in the graph, either by layer or by tag. But I recommend sticking to layers because it is a bit more performant. Below it is a layer mask. Right now we are including everything in the scene, which is fine. The terrain one is pretty self-explanatory. But below it are two options called Rasterize Meshes and Rasterize Colliders, and it may not be obvious which one you should use. The Recast Graph can use either the rendered meshes or colliders as input. Typically, colliders will be faster when scanning or updating the graph, and it is the recommended option if you are doing graph updates during runtime. But using rendered meshes can in some cases be more accurate, since colliders tend to be heavily simplified. However, one advantage to using colliders is that they are solid, so no nav mesh will ever be generated inside of them. In contrast, meshes are just a bunch of triangles, and the system cannot really tell the inside from the outside. We can actually see this if we first scan the graph, and then we switch to using meshes instead. Now, if we scan the graph again, you will see that a nav mesh has actually been generated inside of this box, because it cannot know that this is not actually a valid region for the agent to stand on. So using colliders is typically preferred. So for this tutorial, I will just switch back to using colliders again. Next, there is the agent radius and the rest of the character settings. The radius, of course, changes how much margin there is around everything. So you can see as I increase it, the nav mesh becomes further and further away from all of the obstacles. And the character height, it makes sure that the agent cannot walk below things. So if we take a box, for example, and move that up slightly, then you can see that the agent can right now walk below it. But if we move it down a bit, then the agent can no longer walk under it. And by the way, while I'm editing these settings, I'm continuously recalculating the graph using the shortcut Ctrl-Alt-S or Command-Alt-S on Mac. There's also a max step height. If we take a box and duplicate it to illustrate what this setting does, we can see that if we scan the graph right now, the agent cannot walk between these boxes. But if we increase the max step height a bit and scan the graph again, you can see that now the agent can walk from this surface up to the top of the first box. And of course, there is a max slope setting. And we can illustrate this by lowering it down to a very low value. And then you can see that the second box I created before actually has a slight slope on it. And if we scan the graph right now, you can see that that disappears because it has too much of a slope. Now, this does not apply to stairs, since each individual step will typically be pretty flat. It only applies to sloped surfaces. The rasterization options are perhaps a bit less intuitive. The voxel size is very important, as this is essentially the resolution of the graph. So the sizes of those boxes that everything is voxelized into that I mentioned before. So a smaller voxel size will give you a more accurate graph. And if I change this to 0.1 and then scan the graph, and then you can now see that the graph has straighter lines and perhaps a bit more detail. But a larger voxel size, on the other hand, will make it faster to scan. So if I change this to 1 or maybe 5, okay, maybe 5 was a bit too much, but you can see that the detail is going down. So let me change that back to something more reasonable. Tiling is also pretty important. As you can see, if I reduce the voxel size a bit, and if we look at the graph from above, you can see that the graph is split into several tiles, that you can see here. These are separate parts of the graph that can be recalculated independently, and this is good for several reasons. When you are scanning or updating the graph, it can calculate each tile in a separate thread. So if your computer has lots of cores, scanning or updating the graph will become faster. Secondly, if you're updating the graph during runtime, then you can update single tiles or just a few tiles instead of having to recalculate the whole graph, which makes graph updates much faster. The other settings you typically don't have to change at all, so I'll skip over them here. But you can always look them up in the documentation. And of course, there are also tooltips for each setting if you are curious. Alright, now we have a pretty decent graph, but we can make a few more adjustments to make it even better. One thing you may notice is that right now, the agent is allowed to walk on top of all of these boxes right here. In many games, this may be what we want, but for illustration purposes, let's assume that this is not something that we want. In this case, we can select all of these boxes, and then we can add the Recast Graph modifier component. This component lets you change per object if you want to use a mesh or a collider as a source, or if you want the surface to be walkable or unwalkable. In this case, we want to use a collider and we want an unwalkable surface. So now, if we scan the graph again using the shortcut, you'll see that the nav mesh on top of the boxes disappears. So this is a great way to tweak the nav mesh to your liking. Alright, the nav mesh looks pretty good now, and we are ready to create an agent. To do this, we'll add a new empty game object and let's call it agent. Very creative. To this game object, we'll add the follower entity movement script. There are multiple movement scripts included in the package. The follower entity component is a good all-around movement script that works well for most games and is pretty performant too. There are a few others, and you can read more about them in the documentation, and they have different movement styles, performance characteristics, and so on. So, here is our agent. You can see a visualization of its cylinder shape if we zoom in a bit. And if you are making a 2D game, you can of course change the orientation. We can set this to 2D mode, which will make the agent appear in the XY plane instead. But in this case, we are making a 3D game, so let's switch that back. You will see that there are a lot of options. I'm not going to go through them all in this tutorial, but if you are curious, you can always right-click on them. Let's take this one. And you will see that there is an option called Show in Online Documentation. If you click on it, you'll be taken to the online documentation where you can read all about it. But now we need to ensure that our agent actually has a destination. And this actually requires a separate component, and it's called the AI Destination Setter. So let's type that in and add it to our game object. And this is a pretty simple component. It has a target field. So let's add a sphere to our scene to use as a target. Let's move it to the ground and position it over here maybe. All right, now we can select our agent again and drag it to the target field, our sphere that is. So our agent has a target. And now we're actually ready to go. So let's click play. And you can see our agent is moving towards the target. But let's fix one thing first. We should make sure the agent is visible too. So we can add a cylinder as a child object of our agent. And let's move that to the origin and up a bit. And now our agent is actually visible in the game. So let's play again. And there we go. Now if we move the target around, you can see that the agent is actually following it. Great. If you want to visualize the path that agent is taking, you can select agent and you will see that there are some movement debug rendering options down here. If you select it and you click path, the agent will now visualize its path as it is moving around, like that. Excellent. But if you remember, this is not quite what we set out to do in this tutorial. The goal was for our agent to follow our cursor in the game. And while we are dragging the target around in the scene view, it's not quite the same. So to do this, we'll have to write a small custom script. So let's create a new mono behavior. And let's call it mouse position target, but you can call it whatever. And then we'll double click that to open it up in our favorite text editor. All right, so the first thing you'll want to do is to use the pathfinding namespace. So I'll write using pathfinding at the top. And this will allow the script to reference most of the common classes in the AstarPathfinding project. Next, we'll create a field for our movement script. And then during enable, we can capture a reference to this movement script. Like that. And now during update, we'll want to take the mouse position and fire a ray from the camera to the scene and see where it hits. And if it hits something, then set the destination of the agent to that point. So let's first grab the mouse position. And then we'll convert this to a ray from our camera. And now if we can use the Unity Physics API to check if it hits something. And we'll get a nice hit point out from it. And if it is something, then we can use the destination property of our agent to, set that to the hit point. And now we're done. Setting the destination property will make the agent recalculate its path and move towards this point. So let's save the file and go back to Unity. Now we can select our agent and remove the AI destination setter component because we don't need that anymore, and add the mouse position target script. We will also need to move the camera a bit, because right now the camera is down on the ground, which is not very useful. So let's move it up a bit and rotate it so that we can actually see something. And now let's try it. And there we go. You can see that indeed the agent is following our cursor around. And if we enable path debugging again, we can see that the path is indeed going to our cursor. Perfect. There's one final thing that you may have noticed. Down here, you will see that the agent left a small cut in the graph where it was standing when the game started. And that is because right now the graph thinks that the agent itself is an obstacle. So let's fix that. Remember that in the Recast Graph settings, there was a layer mask. And this layer mask can be used to filter which objects from the scene should be taken into account. So let's remove one layer from it. Now, you'll probably have better layer names than I have. I just have Unity's default layers for this tutorial. But let's remove the transparent FX layer for the sake of this tutorial. And then we can go back to our agent and move that to the transparent FX layer. And now if we scan the graph, you will see that it no longer leaves a mark on the graph. Alright, so that's it for this tutorial. We have covered how to create graphs, how to set up a basic agent, and how to interact with it using a custom script. I wish you the best of luck with using pathfinding in your project.